same, or it may be similar.
It's online.
That was a good one.
Okay. Starting with projectile motion. Projectile motion, I can do this with a little diagram I like to do. Rifle, and it's above the ground here. Here's the ground. And the rifle is horizontal, and we're gonna shoot a bullet.
Mr. Bill, I don't support gun violence.
Well, this is a just pretend gun, okay?
That looks like a,
And we're gonna drop a bullet.
for
also.
real,
We're gonna drop a bullet, we're gonna shoot a bullet.
what kind of gun is that?
It's
Rifle.
22 rifle.
Shouldn't that be like shells or something though?
Yeah, that's a shell out there.
And the bullet is gonna go a mile, and then it's gonna hit the ground. This is 1 mile. Here. Okay. Now, the bullet is fired from the gun at the same time you drop the bullet. Which one's gonna hit the ground first?
When you drop the bullet,
Well, yeah, when you
when you drop.
You said what, the bullet's going a mile and the one that dropped, which one goes faster? The bullet we shooting on when we drop it?
when they
The
decide-
The one that drop gonna fall
decide
first.
that-
But isn't that law that they're gonna be the same?
Thank you. Ta-da. Now, one person paid attention, that's right. Horizontal does not affect the vertical. So this bullet hits the ground at exactly the same time as that one does. It's a mile away, but it's only traveled the same distance vertically. And so it hits at the same time. Okay. So projectile motion involves what? Horizontal and vertical motion. And how do they compare? Whoops.
But that's without like wind drag and everything, right?
Even with wind drag,
So
they should still land at the same time. It won't go quite as far, the wind will make it land sooner horizontally. But vertically, you're going such a short distance that the air friction is negligible, vertically. Okay? So horizontal, you've got constant speed. And vertical, you got what? Yes? Constant acceleration. And I just ran out of room there. That's an N. Can't see that. Constant acceleration vertically, constant speed horizontally. They do not affect each other. They are separate, just like separate motions. When is work done? Well, what's necessary for work to be done? What's the minimum, what's the requirement? What do we have to have for work to be done? Well, what's the formula? Formula is FD equals theta. So if you have a force going this direction, and you have a displacement going in this direction, and the angle between the two is theta, then this is the formula that describes the work done. Now, if they're in the same direction, what's the cosine theta? Well, cosine 0 degrees is 1. Check that on your calculator if you're not sure. Just type cosine 0, and you'll get 1. So if they're in the same direction, you don't really need the cosine. Now, what if you only have force and you don't have direct distance? No work. So for example, if you have a satellite going around the Earth in a circular orbit, then that satellite has a velocity, so it's moving a distance, and it has gravity. Which is at right angles. Well, what does this formula tell you if you have a right angle?
That there wouldn't be any work done.
Right, cosine of 90 degrees is 0. So if the two are at right angles, then there's no work done. And that's great. That means that it doesn't require any work to keep the satellite in orbit. If there weren't any air up there, it would never come down. There is a little bit of air. You never get above the Earth's atmosphere. If you go between galaxies, then there's some places where you might have 1 hydrogen atom per cubic meter. But that's still some mass. Not much, but you never get to 0 atmosphere. I love science fiction, but that's the one era every science fiction story I ever watched is made. They're taking off in their spaceship and saying, well, we just got out of the atmosphere. No, you didn't. The atmosphere got thinner, but you don't ever get completely out of it.
I had a question.
Yes.
The symbol above your force and your,
Displacement.
They're supposed to be arrows.
okay, so they're directional.
This is to indicate a vector. The force is a vector, the displacement is a vector.
Okay.
But work is a scalar, interestingly enough. Even though the two vectors are that you multiply, the two quantities you multiply are vectors. If work is done, what are the possible results? What does work do? There's 3 possibilities.
Is that the energy?
Work and energy are really the same thing. Energy is your ability to do work, so work can cause motion or change motion. So if a body's sitting still, it can make it move. If a body's already moving, it can make it move faster or slower, or make it turn a corner. So there's 3 possibilities here: speed up, slow down, or turn a corner. Now, second possibility is you might store energy for use later. Store potential energy. Now, we've talked about 2 types of potential energy, gravitational and kinetic. And we solved problems using just gravitational potential energy. So I'll list those as an example. Gravitational potential energy is mgh. gravity, 9.8, times the height. We also mentioned, but didn't work with, elastic potential energy. And that's 1/2 kx squared. Where k is a spring constant and x is how far you stretch the spring. So what's the third possibility that work can do?
Change, change the type of energy.
Yes, who said that? Thank you. Change the type of energy, absolutely. Let's give some examples. That was actually was one of our questions on this sheet you just turned in. I hope y'all got it right.
We do
List
too.
3 different forms and types of energy. Give one example of a conversion from each of these forms from one form to another.
I'm looking at that, right?
One example, light. Light comes to us from the sun. When it heats our skin, what does it convert into?
Melanin?
Well, actually, that's true. Yeah, I didn't think about that.
Yeah, I know.
She on a roll today.
I fasted for 3 days, so I'm like,
Okay.
that subconscious just kicked in. I don't even know what it's doing.
You're ready for that A, aren't you?
Yeah, oh yes, I hope so. I'm speaking into existence.
I'm gonna put yours up here too. It can do a chemical energy. Because that's what happens when it creates melanin, it's causing a chemical change. So that's another thing that light can do. Okay? And there's a lot of other things too, I'll just give you examples. What if you go to a concert, you stand next to the loudspeaker, what do you notice? Vibration. So vibration if it's a loudspeaker, it can create sound. And actually a lot of sound. I recommend wearing earplugs if you ever go to those concerts. Because it can damage your ears. And I've been to a few of them.
Where'd you go, Steve?
Close by. What's that place on 7th and Chester? That little restaurant there, they have bands playing in the back room.
Yeah,
Venus.
Vino's, yeah, I've been there a time too.
Mr. Bell.